Hello, my name is Will, and I am a second-year D.Phil student in the Department of Engineering Science. My research focuses primarily on hypersonic vehicles, or more specifically, how we can better use computer simulations to understand their physics. So many people are familiar with the term supersonic, and that relates to the notion of waves moving through the air. So acoustic waves travel at the speed of sound, which at room temperature is roughly 343 meters per second, or about 1,234 kilometers per hour. So for something to be supersonic, essentially just means that it's traveling through the air faster than the speed of sound. What it means for something to be hypersonic is a little bit different. Typically, hypersonic vehicles or hypersonic speeds are defined to be somewhere around perhaps 3 to 5 times the speed of sound. Ultimately, though, it depends on when a certain range of physical phenomena start becoming apparent within the flow. So, for example, when you have a supersonic vehicle, there may form a shock wave in front of the vehicle as it's passing through the air. Now, when air passes through a shock wave, it heats up and it gets compressed. And usually this isn't such an enormous problem. But in the case of hypersonic vehicles, that compression and that heating can actually become so extreme that it can dissociate the air that's moving around the vehicle, and you can actually form chemical reactions simply from the air heating up so quickly. Now, this is just one example, but there are many other physical phenomena that occur when a vehicle is traveling at hypersonic speeds. So in order to simulate the complex interaction of a hypersonic stream of air with a vehicle body that's moving through it, we employ something called computational fluid dynamics. In short, computational fluid dynamics simply means solving a set of governing equations that describe the motion of the air around the vehicle. Now, these equations are somewhat complicated, and solving them can be a challenge, mainly because air can become turbulent. And turbulence is essentially when fluid is moving in a random, chaotic, and high-frequency motion. And at hypersonic speeds, these frequencies can become extremely high. So it's necessary then, when simulating these flows on a computer, to use extremely high resolution and to have to store a lot of information. Something that's useful in understanding these equations is something called nondimensionalization. Nondimensionalization is where we take a number of quantities that describe the nature of a flow, and we arrange them in such a way that all their units cancel out. So in the case of a simple subsonic flow, perhaps we have the density, we have some kind of length parameter, like a radius if you're looking at a cylinder or something. The free stream velocity, or essentially how fast the bulk air is moving. I like to frame non-dimensionalization within the context of simple geometry. So consider these two cylinders. We can describe each cylinder in terms of the ratio between its height and its diameter. So if the ratio is different between these two cylinders, it is impossible for me to uniformly scale one and obtain the other. Now, if I consider that this ratio is very, very small, the diameter to height ratio is very, very small, then I have something like a pencil. If I consider that ratio to be very large, then I have something like a coin. And if it is 1, then I have like a square cylinder, more or less. So this concept of non-dimensionalization is essentially, again, taking all these parameters and arranging them in such a way that you sort of capture the essence of a given object. Now, for fluid flows, there are a number of popular dimensionless numbers to consider. One of the most important ones is the Reynolds number, which I mentioned before. The Reynolds number essentially characterizes how much of a flow is turbulent versus how much of it is laminar, which is essentially not turbulent. Now, for low speed flows over small objects, the Reynolds number is relatively low. For a large object at a moderate speed, the Reynolds number is very high, and for a large object at a hypersonic speed, the Reynolds number is extremely high. In order to simulate a fluid flow over a vehicle, a small region, usually called the domain, is subdivided into a large but finite number of small cells. By analogy, consider an image that you might take with your phone. You can, that image has a certain number of pixels that are used to reconstruct the image later on for later processing. So an image with a low number of pixels doesn't look very good and doesn't capture very much detail, but with a very large number of pixels, you can capture a great amount of detail and reproduce the image quite faithfully. So a natural question to ask is, how many cells do you need for any given simulation? And this is not an easy question to answer. However, the number of cells that you need actually can be thought of in terms of this Reynolds number. If you choose to directly simulate everything within the flow field, then the number of pixels, if you will, that you need scales roughly by the Reynolds number cubed. And for a variety of different modeling assumptions, that scaling can be reduced. So, for example, I work on something called wall-modeled large eddy simulations. And within this framework, the number of pixels or cells that you need for any given flow scales only with the Reynolds number, making it a much more favorable choice. Now, for hypersonic flows around, again, large vehicles, the Reynolds numbers are extraordinarily high, meaning that if you were to try to directly simulate any flow over a real vehicle, then you would vastly exceed the amount of memory even on the largest supercomputer in the world today. While this may be feasible in the future, for now, other methods are needed. One of the most challenging aspects of turbulent flow simulations is what happens near a solid boundary. Near a solid boundary, fluid will stick to a surface and slow down, whereas it's still maintaining its sort of large velocity up away from the body. And so this layer between this slow-moving fluid and this fast-moving fluid is called a boundary layer. And because these interactions are so complex and are so close to the surface, this means that you need to essentially use a very large number of cells right next to the surface of your vehicle. And this can become very, very expensive. Now, within the framework that I use, these complex interactions near a boundary are considered to be somewhat universal. So, instead of using a large number of cells near the wall, I save on computational costs by simply assuming that they are of some form and that they interact with the fluid outside the boundary layer in a very predictable manner. Now, the core of my research here is how to model these interactions. Now, for subsonic flows, these interactions follow some quite regular patterns, but there are a few elements of fluid flows at hypersonic speeds that can challenge these interactions. One of them, for example, is the interaction of a strong shock wave and this so-called boundary layer. The shock wave can change how these interactions happen very, very rapidly, and this can challenge the models quite a bit because they do not have those assumptions built into them. Another challenging aspect is, as I mentioned before, when the fluid passes through a strong shock wave, it can heat up so much that it causes dissociation of the air, and that can actually have a strong impact on these interactions near the boundary as well. Now, these interactions near the boundary are extremely important when considering the design of a hypersonic or even a subsonic aircraft or vehicle. These boundary interactions govern how much drag is applied to the vehicle by the fluid, as well as how much heating is applied, as well as the aerodynamic forces that are experienced by a vehicle flying through the atmosphere. Many of the models that exist today for these near-wall interactions are not suitable for the complex flows around hypersonic vehicles. If I can be successful in developing a model that does perform well for a complex hypersonic vehicle, then it will be feasible to reduce the cost of high fidelity simulations of real hypersonic flight hardware.